It's the critical part. Yes.
Okay, we are recording now. So
Okay.
welcome everyone.
Yes, target. I mean, the target will always feel a point at some point in time, but if it's low, then the target will somehow.
Our speaker from University College London, Debarshi, has been talking about testing quantumness of gravity. So this is the second part of the talk. So Debarshi, to you and also the other participants, if you want to ask any questions, just unmute yourself and
That
ask.
is that will require a lot of more work and it's one other thing.
Yeah.
It's very important.
Yeah, sorry for the inconvenience. And since I'm using my mobile network, if there is any network problem, just call me in WhatsApp to let me know. Okay, so last week I discussed a bit about some experimental proposal to test quantumness of gravity. And today I will further discuss this topic. So before starting anything new, let me just recapitulate a bit of my yesterday's talk. So yesterday, last week. So last week I discussed that a lot of work has been done till date to construct quantum theories or classical theories of gravity sourced by a quantum mass. But it is very difficult to verify these theories in experiment. In fact, verifying this theory requires very high amount of energy, and it requires creating a particle detector of the size of our galaxy. On the other hand, we address a much easier question, whether gravity is quantum at all. And we still don't know whether gravity is quantum or classical. And addressing this question seems to be easier through a laboratory-based experiment. So, to address this question, two papers in 2017 came out, which proposed a realizable experimental scheme to test whether gravity is quantum. So, the idea is that two masses are held initially in product state, and if after a certain time entanglement is generated between these two masses, then it can be concluded that the mediator or the interaction between these two masses is non-classical in nature. And by experimental design, it can be ensured that the dominant interaction between these two masses is gravity. That will mean that the generation of entanglement in this experimental setup will imply that gravity is non-classical in nature. This comes from the argument of the well-known principle that local operation and classical communication cannot entangle. And here there is an assumption that one assumption is there that any interaction is assumed to be local in nature. That means the interactions are not action at a distance type non-local interaction. It is assumed in this type of experimental proposal. And in fact, any interaction in nature, other interactions in nature, electromagnetic interaction, weak interaction, strong interactions, these are local in nature. And also the locality assumptions is motivated from general theory of relativity. One thing I forgot to mention yesterday. So here I told that if entanglement is generated, then it will be concluded that gravity is non-classical. Now we have to estimate whether entanglement will be generated if gravity is quantum. And in 2017 paper, it was shown that if we start from a product state of these two masses, at the end we will get an entangled state between the two masses. But in order to derive this final state, the interaction between these two masses was taken to be Newtonian interaction. So the question comes whether Newtonian interaction, using Newtonian interaction is justified, because Newtonian interaction is a classical concept. And Newtonian interaction is action at a distance interaction. It is non-local interaction. However, Taylor and Jacob Taylor and other people have shown that if you want to construct a quantum theory of gravity, then in the low energy domain, just using the Newtonian potential as the Hamiltonian and converting the potential into an operator form is sufficient. So this justifies the use of Newtonian potential. So here the form of Newtonian interaction is taken, but Newtonian interaction is Gm1 m2 by r, but the r is taken as an operator. And this usage is justified from quantum field theoretic approach. People have justified this use. So, okay. So, last week I was asked to discuss about two papers, which is related to this experimental proposal. So, before going into further details, I will like to discuss these two papers.
Okay, so what we are seeing here is
so the first paper is this paper from Lamy, Julen, and Martin Plain. So it discusses testing quantumness of gravity without entanglement. The proposal that I discussed last week relies upon observing entanglement generation due to gravity. But it is known that these people have shown that the entangling operations is a strict subset of the set of operation realizable with velocities. So this is the Venn diagram. This is don't expect anything, any geometrical property of these two sets from this diagram. So there are operations which cannot create entanglement, but which can also not be explained in terms of local operation and classical operation. For example, the swap operation. Consider two spatially separated parties, Alice and Bob. Alice's state is psi and Bob's state is phi, and they are in product state. And the swap operation just swaps this state. So after this operation, Alice's state becomes phi, and Bob's state becomes psi. But this operation cannot be realized with local operation and classical computation. And also, entanglement is never generated in this operation. So this is a non-entangling operation which cannot be explained by velocities. In fact, this operation requires quantum information processing between the two parties. So the key conclusion is that even if we can't show gravity-induced entanglement, then also proving that the effects of gravitational interaction can't be simulated by local operation and classical communication would imply that gravity is non-classical, assuming locality of interaction. So, in order to further proceed, these authors have figured out some of the constraints that every LOCC model should obey. And this gives rise to the LOCC inequality. These are like Bell type of inequality. And violation of this LOCC inequality will imply that the underlying dynamics is non-LOCC. Then this result was applied in the context of gravity to probe non-classicality of gravity without generating entanglement. And since entanglement generation is not involved, this type of experiment may be less difficult. So one example, this is a toy model. This is not a realistic example. Consider two identical quantum harmonic oscillators with masses m and frequency omega. And each of these harmonic oscillators are oscillating with, along the same straight line, whose centers are separated by a distance t. Assume that the two masses interact only through gravity. And also let us assume that gravity is quantum. Then if we start with this product of coherent states, that means two harmonic oscillators are prepared in coherent states and they are taken in a product form. Then under certain conditions, if the system is evolved under gravity, then the final state takes this form. This final state is again a product of two coherent states, and this is not an entangled state. Now, suppose in experiment, in experiment we don't know whether gravity is classical or quantum. We observe this dynamics that starting from the product of two coherent state under gravitational evolution, we observe a different product of two coherent states. Now, it can be shown that the above dynamics violates LHC inequality. That means the dynamics preparing the underlying this evolution cannot be explained in terms of local operation and classical combination. And since this state transfer is happen under the effect of gravity, this will imply that gravity is non-classical, assuming locality of gravitation. And note that this dynamics does not create any entanglement. That means without creating entanglement, you can show non-classicality of gravity. And in fact, for a particular choice of this parameter, this operation becomes a swap operation. And as I mentioned earlier, swap operation is a non-LHC operation. That's why it violates the LHC. So this is the key result of this paper. Next, I would like to discuss another recent paper by Navaskas. Yeah.
I'm a little bit curious about this LHC inequality. So finally, when you get this state on the right-hand side,
yes.
So after that, you perform some measurements, right? Otherwise, so it is also something like Bell inequality.
Yes, right.
Then, I mean, what do you check? Do you do full tomography of this thing to check that whether it is of this form or not, or something like that?
Okay, so the LHC inequality is in the form of fidelity. Hypothetically, we assume that gravity is quantum. Then we can theoretically write down what will be the final state. We can figure out which will be the final state if gravity is quantum. That is our desired state if gravity is quantum. But in reality, we will get some other state.
Of course.
So we will evaluate the fidelity between the actually prepared final state and the hypothetically predicted final state is if gravity is quantum. We will calculate the fidelity.
So it is like a measurement on the right hand side, like for the right hand side state. You will take this, whatever you expect, you take the basis on Alice's side and a different basis on the Bob's side. I guess and then you perform some measurements and see that what is the overlap of
Yeah. And the base, it is not Alice's local measurement, Bob's local measurement. It may involve joint measurement.
Okay. But then how do you? Okay, so
you need the information about the joint measurement, right? A joint state, joint final state.
Yes.
So local measurement may not suffice.
Okay, so you say that final measurement has to be done on both of these together.
Yes. It may be separable measurement sometimes, but in general, it can be entangled measurement.
Okay.
Then you extract the information about the final state.
So although the states are not non-local right now, but the measurement could be non-local in that sense.
Here I am writing down this state just from theoretical calculation. In reality, you may not know whether the final state is entangled or separable.
Yeah, of course.
You don't know.
Of course. But that is the expectation. So the gravity actually works as you have assumed, then this should be the state. So there is no non-locality in the state, so it is just product state. And then finally you perform some measurement
Yes.
get some statistics,
It's
and this measurement
Yes.
cannot be
equation 28 basically with sigma z.
Yes. From those statistics, I will calculate the fidelity, and if the fidelity is below a certain bound, then I can tell the LOCC inequality is valid.
In the code, yeah, in the code or in physics.
And actually, here I have started with two pure coherent state. And the
Right.
same for the same
Yeah,
dynamics, if you start with a product of two squeeze states, then the final state will be an entangled state. So depending on the initial state, at the end you will either get product state or
Inverse, I
entangled
guess, yeah.
state. And in experiment, you don't have any control on the initial. You want to prepare this state,
Yes.
but there will be noise.
Yes.
So you may
Right.
you will not end up
That's why it's
preparing
like
this
if you
ideal
allow it to
state.
happen for enough amount
So,
of time, it's-
In experiment, the final state may be
and this is
entangled
order system, just tell you
or
why
maybe
the
separable.
graphs are different, because-
Okay.
And it's a
Okay.
negative.
Okay.
Negative.
Please continue.
Debarshi,
Yes.
Debarshi, actually, I don't know whether I'm doing any mistake or not. In one of the slides, when you are talking about the subset relationship between velocity and non-entangling,
Normal entanglement gives you that.
before this, so what I'm saying is, you said that the set of entangling operations is a strict subset of the set of operations realizable with.
LOCs. No.
No,
Sorry.
no, it's, what I'm saying is it should be the other way around. That is what I'm trying to say.
Right. Sorry. Strict subset of the set of operation not realizable with LOCs.
Not realizable. Yes. That is what I'm saying. Yes.
Yeah.
But actually,
It is non-LOCC operation.
Yes, non-entangling operations is a strict superset of LOCC
Yes.
operations.
Yes.
Yeah.
It
Okay,
is non-LOCC operation.
Yes. Okay.
Swap operation, for example, swap operation lies in this region. It is non-LOCC operation, but it cannot create entanglement.
Yes, it is non-LOCC, but it is non-entangling.
Right. Yeah, there is a mistake.
Debarshi, just to clarify, so what does this violation of LOCC inequality would tell us?
That the underlying dynamics cannot be explained by local operation and classical communication.
Okay. Thank you.
And
It
if the
doesn't tell about whether the dynamics is unitary or.
No. It
Okay.
is just LOCC.
Okay. Thanks.
Then you try to figure out. Well, I'll look at the graph again. Now I understand what the graph is.
Okay, the second paper that I would like to discuss is this paper. It is a recent paper by Navaskas. So here, the authors have shown that Diossi-Penrose model of classical gravity predicts gravitationally induced entanglement. So I will just discuss this result very brief. So the Diossi-Penrose model was proposed by Lajos Diossi and Roger Penrose. It is a modification of standard quantum mechanics. And this model attempts to address the quantum measurement problem. It also explains the issue of quantum to classical transition as we go from microscopic system to macroscopic system. So very heuristically, the Diossi-Penrose model, the dynamics can be expressed in this form, where the dynamics has a unitary part as well as a stochastic non-unitary part. This part is mathematically introduced by Diossi, and later Penrose explained it from physical point of view. So if the mass of the system is very small, then in this dynamics, the unitary part becomes dominant. That means this part does not contribute. And so the standard quantum mechanical formalism is reproduced. However, if the mass of the system is large, then this stochastic non-unitary part becomes dominant. And this part causes gravity-induced collapse of a spatial superposition of mass. Spatial superposition I explained last week, that mass being here and there simultaneously. So due to this stochastic non-unitary part, this stochastic non-unitary part has some contributions from of the gravitational field of the mass, And when the mass is large, this stochastic non-unitary part becomes dominant and it causes gravity-induced collapse. That means when the mass becomes very large, the gravity performs some measurement on the superposition, spatial superposition of mass, and that causes collapse of the superposition. So in this model, the collapse as well as unitary dynamics can be explained using a single equation. And you can also explain why we don't see superposition of a large mass in reality. So this is the model. So in this model, actually gravity acts as a global measurement channel acting over the whole spatial distribution of a mass. That means gravity is not a local interaction in this picture. And this is actually a major drawback of this model. And people have criticized this model for this drawback. And since gravity is a non-local interaction in this model, it is non-LHC. And that means gravity-induced entanglement generation is possible in this model. And also entanglement generation in this model can be explained in a different way. So the Diosy-Penrose model was, the physical interpretation of Diosy-Penrose model was given by Penrose. And the Penrose's interpretation is like that. Suppose you create a spatial quantum superposition of mass, and that will create superposition of different space-time curvature. That means quantum gravity is valid in this domain. Now, if mass is large, then the superposition of different space-time is unstable and decays in time by some mechanism that was designed by Penrose. And the mechanism depends on energy momentum uncertainty relation. And since the superposition of different space-time collapses, it makes the system wave function also collapse. That means in this domain, classical gravity is valid. But this is not the case.
Wait, Debarshi, Orko, are you trying to say something, or maybe you can mute yourself?
Means that it's going to be more than far away.
Hello?
If when you make this perturbation, that's going to be influenced locally more than far away.
Okay,
That's why you have it.
I think you can mute someone, right?
But yeah, here, so one thing though, if you take a box,
Yeah, host can mute someone. So Shomda, if you can, I think, Orko, there is some problem.
Yeah. So in Diosy-Penrose model, gravity is not always classical. It is initially quantum when the mass is in superposition. But when gravity-induced collapse happens, then gravity becomes classical. So it is not appropriate to say it is a classical theory of gravity. Yeah, this time scale may be very small. The time scale for quantum gravity may be very small. But it is not a classical theory of gravity for the whole time. This is not the case for other classical theory of gravity. For example, the newly proposed classical theory of gravity by Oppenheim. In Oppenheim's theory, gravity is always classical, even when the source mass is in spatial superposition. So the Diosy-Penrose model can be pictorially represented in this figure. I have taken this figure from this paper. So here it is shown that if the mass is in spatial superposition, here plus there, then the space-time curvature is also in superposition. Then if the mass is very large, then the space-time superposition collapses, which collapses the mass spatial superposition of mass. So at the end, you will get a definite distribution of the mass in the space-time, and the space-time is also in a definite configuration. And if the mass has some charge, it will emit some electromagnetic radiation. And from that radiation, one can experimentally verify the dioxide, Penrose dioxide model. But the main point is that when the mass is in superposition, the space-time is also in superposition in this dioxide model. Now, in this new paper by Navaskas, they actually have mathematically used the dioxide model dynamics and mathematically shown that entanglement can be generated if there are two masses, and if each of these two masses is in spatial superposition. So this is the wave function of the first mass. It is in spatial superposition. This is the wave function of the second mass. It is in spatial superposition. And if you apply the dioxide model, then entanglement will be generated after certain time. But they have not explained anything physical, any physical interpretation about it, or they have not explained this phenomena from the physical interpretation of the dioxide model given by Penrose. And as I mentioned earlier, since in this picture, gravitational interaction is non-local, entanglement generation is possible. And also, they have shown that in their paper, they have shown that gravity-induced entanglement will be there as long as the spatial superposition of each of these two masses is not destroyed.
Makes sense. It's fine.
But as I mentioned earlier, if the mass is in spatial superposition, then the space-time is also in superposition. That means during this experimental timeline, the space-time is in superposition, which implies that the gravity is quantum in this regime. And since gravity is quantum, entanglement generation is not surprising in this picture. So to summarize, gravitational interaction in the Diosy-Penrose model before the collapse happens is a non-local operation, quantum computation. And there is
It's still a straight line, right?
nothing surprising that it will generate entanglement. So at the end, I would like to mention that this title is quite misleading. They have mentioned in their title that Diosy-Penrose model of classical gravity, but the regime they considered, in that regime, gravity is not classical, and their final conclusion is also misleading. They mentioned that our results prove that experimental demonstration of gravity-induced entanglement are insufficient to conclude that gravity is fundamentally quantum. But as I have discussed, that their argument is not justified. So I hope now I will proceed to my topic. Okay. So last week I discussed the 2017 proposal to test quantumness of gravity through witnessing gravity-induced entanglement.
So that's called intact.
But in that protocol, if the decoherence rate is above a certain threshold, then it can be shown that no entanglement will be generated in the protocol. Using PPT criteria, you can show that, because these are entanglement between two qubits. So using PPT criteria, you can show that no entanglement will be generated if the decoherence rate is above a certain threshold. And if no entanglement is generated, that will imply that the protocol will fail. However, for such high decoherence rate, every decoherence has some adverse effect on superposition. But even for such high decoherence rate, though the spatial superposition will be affected, it will not be completely destroyed. So the question remains, can this remaining superposition or coherence be exploited to observe some other non-classicality of gravity? Next, the 2017 proposal requires realizing certain entanglement witness operators, because at the end you have to witness entanglement. And witnessing entanglement requires completely trusted measurement devices, for example, Pauli measurements. But in experiment, it is very difficult to realize exactly these measurements in every run of the experiment. However, one can bypass this requirement by detecting entanglement through Bell test.
Yes.
But Bell test is more demanding than entanglement witness test because it requires even lower decoherence rate, because not all mixed entangled states are Bell non-local. And also Bell test involves a lot of loophole, and closing those loopholes are very difficult. So the question arises, can we propose a new experiment to test some non-classicality of gravity that does not require trusted measurement devices? And at the end, in these two papers by Carlo Rovelli, Kassler-Bruckner, they have shown from quantum field theoretic approach that if entanglement is witnessed in the 2017 proposal, it will imply that the space-time curvature obeys quantum superposition principle. But quantum superposition principle alone does not define quantum mechanics as a whole. So even if we get some positive outcome in this 2017 experiment, in the experiment of this 2017 proposal, then also we cannot conclude that gravity is quantum. At best, we can conclude that gravity is non-classical, that obeys superposition. To know whether gravity is quantum at all, we have to test more and more quantum mechanical postulates in the context of gravity. From these motivations, we propose a new experiment to test quantumness of gravity. And the key aspects of these new proposals are it works for any finite coherence rate. It does not require trusted measurement devices. And it tests a specific aspect of quantum measurement postulate, which is different from quantum superposition principle. So what do we mean by quantum measurement postulate? Quantum measurement postulate can have several parts. There is quantum measurement induced collapse or disturbance, and this particular aspect we aim to test here. There is always one measurement outcome in a single run. It is always observed. There is nothing quantitative to test here. And the outcome probabilities are given by Born rule, but we are not able to test Born rule in the context of gravity.
Then we'll look at the differences of those quantities.
So I think I explained this vague idea about our experiment last week. Okay, so everyone knows double slit experiment. So in double slit experiment, if an electron is subjected to a double slit, then interference pattern will be observed. But if you perform which path measurement before the electron hits the screen, then the interference pattern will disappear. This is due to quantum measurement induced collapse or disturbance. Now, our idea, our proposal is almost similar to that. In the first part of our proposal, we will do the double slit experiment with electron. In the second part of the experiment, instead of measuring performing which path measurement, we will perform gravitational field of the electron. And if this measurement causes disappearance of the interference pattern, then we can conclude that gravity is non-classical. How? Because this phenomena can be explained in this way, that this measurement of so here the electron is in spatial superposition, that is creating superposition of different space-time curvature. And when you are measuring the gravitational field of the electron, it collapses the superposition of different space-time curvature, which in turn collapsing the mass distribution of the electron. That's why you will observe disappearance of interference. This is a consequence of Einstein field equation, that distribution of mass determines the space-time curvature, and on the contrary, the space-time curvature determines the mass distribution. So if you disturb the gravitational field, it will in turn disturb the mass distribution. But this is a very vague idea. In this experiment, electron has very in this diagram, electron has very small mass, so its gravitational field is very weak, and it is almost impossible to measure the gravitational field of an electron. And also, it is very difficult to ensure that the measurement you are performing is indeed on the gravitational field of the electron. You have to cancel all other interactions, between the electron and the measurement device. And that is very difficult for an electron and for a double slit experiment where the electron goes through free space. You don't know the exact path of the electron. So to formulate this experiment, we need few concepts. So let me first define what do we mean by classical field. So classical field is number valued at each point in the space-time. So at each point in the space-time, there is a number. And one can, in principle, measure those number values arbitrarily accurately without any disturbance. This is very common in our classical world. In our classical worldview, we can perform measurement arbitrarily accurately without causing any disturbance. And these two conditions give rise to the non-disturbance condition of classicality. It tells that the act of performing an intermediate measurement should not influence the outcome statistics of a subsequent measurement. So, for example, if you observe a football match, your act of observation should not have any effect on the result of the football match. So, this is very common in our classical world. But there is a caveat. So classical system can be measured in principle without disturbance. But in practice, measurement on classical system can also cause disturbance. This is called classical disturbance. For example, if you want to observe the position of a classical particle by shining light, then the photon can impart some momentum, which in turn can change its position. So in this case also, classical measurement on a classical system is causing a disturbance. But that disturbance is not, classical disturbance is not a quantum feature. It can be explained classically. And this disturbance is not an inherent part of classical mechanics. And there is always a possibility that you can reduce such classical disturbance arbitrarily. You can make this disturbance arbitrarily small in experiment. On the other hand, quantum measurement induced collapse or disturbance is an inherent part of quantum mechanics. It is a postulate of quantum mechanics. And there is no way you can reduce or eliminate such quantum measurement induced disturbance because it is a part of quantum mechanical postulates. So violation of the non-disturbance condition that I explained earlier, or NDC, is a consequence of measurement-induced disturbance. And in experiment, if you can show violation of this non-disturbance condition after eliminating all possible classical disturbance, then it will imply that the disturbance due to measurement that is happening is purely a quantum feature, because you have eliminated all possible source of classical disturbance. This is the key concept behind our proposal. So in experiment, how to test the non-disturbance condition, you prepare a system and its associated field, then it evolves for a certain time. Then you perform an intermediate measurement, observe the outcome. Then after certain in the system and the field evolves for a certain time, then you perform a final measurement and observe the outcomes. And you repeat this experiment in many rounds. In this case, the intermediate measurement and final measurement may be different. And each measurement is either on the field or on the system. Now, in this experiment, sometimes you perform intermediate measure. In some runs, you perform intermediate measurement. And in some other runs, you don't perform this intermediate measurement. Everything else remains the same. In this picture, if the final outcome statistics without any intermediate measurement, okay, so the non-disturbance condition tells that the final outcome statistics in the absence of this intermediate measurement should be equal to the final outcome statistics after intermediate measurement. Because the non-disturbance condition tells that this intermediate measurement can be performed without any disturbance. So it does whether or not someone performs this intermediate measurement should not have any influence on the final outcome the outcome statistics of the final measurement. That's why the final outcome statistics of the final measurement without the intermediate measurement and after the intermediate measurement should be equal. So now let me explain our proposal in a more concrete form. So for that, we need the concept. Yes.
I just needed one clarification that you need these intermediate measurements to be of different kinds, not a fixed intermediate measurement. Because I see that there is some input X which can change the intermediate measurement, or is it just presence or absence of the intermediate measurement? The X
Yeah.
input.
Yeah. Sorry, can you tell this
I'm asking
intermediate
that
measurement?
X input, it
Yes.
means that input X, it means that you have to perform different intermediate measurements, or it is just that it is the presence or absence of the intermediate of a fixed intermediate measurement.
Oh, it is X is fixed. It is just you either perform X or does not perform X.
Okay, so it is the presence or absence of the intermediate measurement. Okay.
Yes, yes,
Okay.
yes. Y is also fixed.
Oh, okay.
In every run, X and Y are fixed.
Okay.
Debarshi, so A is the intermediate measurement, which is the measurement of the gravitational field.
Yeah,
And final measurement
in our proposal we will do that, but I have not discussed it till now.
Okay.
Okay, so to discuss our proposal in a more concrete way, I need the concept of Mach-Zehnder interferometer. So the Mach-Zehnder interferometer is a refined version of double slit experiment. Here a particle is subjected to, so in double slit experiment, the particle can propagate through free space. On the contrary, in the Mach-Zehnder interferometer, the particle can propagate through fixed path, not anywhere in between. And in double slit experiment, the particle can hit the screen anywhere. On the other hand, in the Mach-Zehnder interferometer, there are two fixed detectors which can collect the particle. Now, if you perform the double slit experiment with a sand, then no interference pattern will be observed because you cannot create superposition. In reality, you cannot create superposition with the sand particle, which is equivalent to this Mach-Zehnder interferometer experiment, where at the end you will get both the outcome plus and minus with half of probability. On the other hand, if you perform the double slit experiment with electron, you will observe an interference pattern, which is equivalent to getting this type of probability in the Mach-Zehnder interferometer. Here, plus probability will be obtained with probability 1, and in this detector, no particle will be detected. So this is the concept of Mach-Zehnder interferometer. Now, in our proposal, we will subject a mass through a Mach-Zehnder interferometer we will end through a Mach-Zehnder interferometer. And at the end of the Mach-Zehnder interferometer, we will observe the outcome plus or minus. This is one part of the experiment. In the other part of the experiment, in the other part of the experiment, we are ensuring we are doing the same, except we place a detector in the midway of the interferometer that performs measurement on the gravitational field produced by this mass. So here we are assuming that the mass is quantum mechanical. That means you can prepare this type of spatial superposition with this mass, but it is large enough such that it can produce a detectable gravitational field at the position of this detector. And the second important point is that this intermediate measurement is on gravity. It is not a position measurement of this mass by electromagnetic radiation or by photon scattering. It is indeed a measurement of the gravitational field of the mass. Now, if gravity is classical, then according to the definition of classicality, this intermediate measurement of gravity should not change these final outcome statistics. That means NDC should be satisfied, which is written in this form, that the final outcome statistics in this first picture, where no intermediate measurement performed, should be equal to the final outcome statistics in the second picture, when an intermediate measurement on the gravitational field is performed. On the other hand, if in this picture non-disturbance condition is not satisfied, then it will imply that gravity is non-classical, because it will imply that this intermediate measurement on gravity is causing some disturbance that is getting detected in the final outcome statistics. Now, the actual proposal does not involve, obviously, Mach-Zehnder interferometer, because Mach-Zehnder
just a small clarification. I mean, so this measurement of this gravitational field, so it is being performed at a definite position, right?
Yes, yes.
So does it matter if you change the position or something like that, or is it okay to measure anywhere? Like
In this schematic diagram, I'm just assuming that this measurement only performs, this detector only measures gravity.
no, gravity.
How or
You said like it is like a field, right? I mean, so you can
Yes, yes.
measure it at different positions, like different points in the space-time. So
Yes,
I
yes.
mean,
But the position is important in order to ensure that this detector does not perform measurement through electromagnetic radiation or photon scattering. To ensure that the position of this detector is important, that I will explain in the next slide.
okay. Please proceed.
From this slide, it is difficult to answer. So in the actual experimental proposal, we cannot, in the actual experiment, we cannot use Mach-Zehnder interferometer, because last week I mentioned that Mach-Zehnder interferometer requires transmission with some probability, reflection with some probability, and transmission relies upon quantum tunneling, and for large mass, the quantum tunneling does not happen. The transmission probability is very low for large mass. So though for small mass, those interference experiment or superpositions are done with Mach-Zehnder interferometer, for large mass, for which the gravitational field will be strong enough, you cannot do this experiment with Mach-Zehnder interferometer. So here we will again consider, we will again take the help of Stern-Gerlach interferometer that I explained last week. So here each mass has some embedded spin, and you are creating spin superposition initially, and then the mass with spin is subjected to some inhomogeneous magnetic field. And this, since the spin is in superposition of up and down, the mass will proceed or will move in a superposition of this path and this path. So in this way, in the first part of the experiment, the spatial superposition of mass will be created. At the end, by reversing the direction of the inhomogeneous magnetic field, or in practically, it is easier to flip the spin by some microwave pulse. So either by flipping the spin or by inverting the direction of inhomogeneous magnetic field, we can revert the motion of the two masses, revert the motion of the mass that will close the interferometer. And at the end, this I explained in last week. Initially, the spin is in superposition. Then there will be a path spin entanglement, and which is creating the path superposition. And at the end, due to entanglement swapping, the path degrees, the information about the path degrees of freedom will be transferred into the spin degrees of freedom. And at the end, we will perform a measurement on the spin of this mass. This is the first part of the experiment. In the second part of the experiment, everything remains the same, except we place two sequential probe mass in the midway of this source mass interferometer. And each of these probe mass is again prepared in spatial superposition by Stern-Gerlach interferometry. So each of these probe mass, which is denoted by small m, has some spin, and they are again subjected to Stern-Gerlach inhomogeneous magnetic field. So you create a spatial superposition. At the end, you close the superposition, and you perform a measurement on the spin of these small elements. After this first probe measurement, the first probe mass is discarded, and you start with another probe mass. And this second probe mass is again subjected to Stern-Gerlach interferometry that will create spatial superposition at the beginning. Then at the end, the superposition will be closed, and we perform measurement on the spin of the second probe mass. So these two intermediate measurements are there in the second part of the experiment. Now, if we consider quantum gravity, that means if we consider that in the low energy domain, we can, as I mentioned earlier, we can take Newtonian potential, but we have to take operator form of Newtonian potential. If we take that, then it can be shown that the final outcome statistics in this case will be different from the final outcome statistics in this case. And it will be a function of the gravitational constant, mass of the source mass, mass of each of the probe mass, the distance between the source and the probe, the superposition size, and the interaction time. Now, so you will indeed get some violation of non-disturbance condition if gravity is quantum. Now, here we have to ensure that the distance between the source mass and probe mass is such that the dominant field in the dominant interaction between the source and the probe is gravity. And following my discussion the last week, this can be done if we place the probe and source and the probe mass at this type of distance. Then gravitational field of the source mass will be dominant at the position of the probe mass. And since the probe mass does not interact directly by contact with the probe mass, or does not interact by electromagnetic radiation or by some other means, it interacts only through gravity. The probe mass interacts only through the gravitational field of the source mass. That means this measurement of spin of the probe mass is actually a POVM or generalized measurement on the gravitational field of the source mass. Because by performing this measurement, you can have the information about the relative phase that has been accumulated during this gravitational interaction between the source and the probe mass. So it is indeed a measurement on the gravitational field of the source mass.
Yes, I have drafted something and then I will sit down.
In terms of the language of graviton, if you consider quantum theory of gravity, this mass is getting entangled with a graviton, and that graviton is getting entangled with the probe mass. And the probe, it is actually gets entangled with the position degrees of freedom or spatial degrees of freedom of probe mass. But since the information about the position degrees of freedom is transferred to the spin degrees of freedom, so the information about the graviton can be extracted by performing measurement on the spin of the probe mass. So this proves that these intermediate measurements are indeed on the gravitational field of the source mass, and it can be ensured experimentally by choosing appropriate parameter. Okay.
Debarshi, I have a small question, like maybe you have explained, but I have missed that why do you need these two probe masses? Why
Yeah,
can
I
you
will
not
tell.
do
I will tell in the next slide. So, as I mentioned earlier, that in order to conclude about non-classicality from the violation of non-disturbance condition, you have to ensure that there is no classical disturbance, right? Now, if there is one probe, the measurement on the by the first probe
there are a lot of big figures.
is actually if you place the first probe, there will be some gravitational interaction between the first probe and the second probe.
Yeah, let's track back to the
And,
finish what we were discussing about.
Actually, measurement is nothing but only this dephasing part. With some probability, the state will be decoherent. With some probability, the state will not be decoherent. So that means with some probability, you apply sigma z rotation on the system. With some probability, you don't apply anything. But if there is only one probe, there is one deterministic rotation along with the stochastic rotation. Measurement is nothing but if you measure and average over all outcomes, then that is equivalent to stochastic rotation on the measured system. But if there is only one probe, there is one deterministic rotation along with the stochastic rotation. This part is causes the measurement. This part does not have, this deterministic rotation does not have any link with measurement process. It is just because you place the probe and due to the gravitational attraction, a constant phase is generated in the source mass. And that phase does not have nothing to do with measurement process. But this phase mass, so you can explain this phase mass as a classical disturbance. It is just because of the presence of the probe, a phase is developed in the source mass. So you have to eliminate such classical disturbance. So if you, instead of one probe, if you take two sequential probe, then the effect of this deterministic rotation, which is a classical disturbance, will be eliminated. Because this deterministic rotation is nothing but a sigma z rotation. And since sigma z square is identity, two sequential application of sigma z will be identity. So for one probe, there will be some classical disturbance, but the classical disturbance due to the first probe will be eliminated by the classical disturbance due to the second probe. That's why we have taken two probes in order to eliminate classical disturbance. There may be some other means to eliminate classical disturbance, but we have taken this one approach. And classical disturbance, when this classical disturbance can happen, if there is some interaction between the source and the probe, classical disturbance due to other means, that means electromagnetic interaction, photon scattering, will be eliminated by ensuring this type of distance or putting a screen between the source and the probe. So the only classical disturbance that we have to bother is about due to gravitational interaction. And the classical disturbance due to gravitational interaction we have eliminated by considering two sequential probes. So in this way, you can eliminate all possible classical disturbance. So what are the key aspects of this proposal? Here we can show that the non-disturbance condition violation persists for any finite decoherence rate, which was not the case in 2017 proposal. Obviously, with an increase in the decoherence rate, the magnitude of the NDC violation decreases, but this can be offset by increasing the number of runs. If the observable violation or if the value of a probability is very small, that can be experimentally verified statistically reliably by by performing larger number of experimental runs. So if the magnitude of NDC decreases, that can be managed by increasing the number of runs. Also, in this protocol, it does not depend which particular measurement we are performing on the probe or which particular measurement the probe is performing. It does not matter which particular measurement the probe is performing, because for any measurement by the probe, if you observe some disturbance, it is sufficient to tell about non-classicality of gravity. So it does not require trusted measurement devices. On the other hand, in 2017 proposal, entanglement weakness was involved, and that requires trusted measurement devices. And also, entanglement generation between the source mass and the probe mass is not necessary in this case. Though I have explained it in terms of gravity. When I was explaining it in terms of graviton, I told that the graviton will be entangled with the source mass and the graviton then will be entangled with the probe mass. That means the source and probe mass will be entangled. But, and in fact, considering Newtonian potential in the operator form, if you, in our paper, we have shown the mathematics, it is there that the source mass and the probe mass is getting entangled, which is quite similar to the earlier proposal. But that entanglement generation is predicted from quantum theory of gravity. But suppose there is some hypothetical non-classical theory of gravity that does not generate entanglement, and we have actually given an example in our paper. But that hypothetical non-classical theory of gravity correlate the source mass with the probe mass. That correlation is weaker than entanglement. In that case also, the measurement on this probe mass will give some information about the gravitational field of the source mass. So entanglement generation is not necessary in this protocol. So it is also, that means it is independent from the 2017 proposal. So taking realistic parameters, where we have taken 10 to the power minus 14 kgs of mass, the distance we have taken 157 micron, that will ensure that the measurement by the probe mass is indeed on the gravitational field, because other interactions or other fields are very weak compared to the gravity in this region. With this parameter regime, for a range of values of superposition size and for a range of values of the interaction time, we can get quite large values of NDC violation. So currently, experiment for both the proposal, the initial requirements are the same. You have to prepare spatial superposition of a large mass. So currently, experiment is going on in collaboration with experimentalists worldwide. So where we are now, as I mentioned earlier.
Debarshi,
Yes.
I guess we don't have much time for this meeting.
Yeah, I'm just finishing it.
So if you want to continue.
No, I am finished. I have one more slide. Just one more slide.
Okay, because people are also leaving, so I guess.
Yeah, just one more slide. So this type of mass has already been prepared in pure state. That's why this type of experimental proposals are realizable with near-term technology. But after preparing the pure state, you have to prepare the spatial superposition. That is the first challenge, that you have to prepare a spatial superposition using complete Stern-Gerlach interferometry. Recently, this has been achieved with smaller masses, but we have to increase the mass again. So to conclude, if entanglement is detected in the 2017 proposal, or if NDC is violated in our new proposal, that will rule out all these possible classical theories of gravity. It will not tell which particular quantum theory of gravity is correct, but it will rule out all these type of classical theories of gravity. So to conclude, whether gravity is quantum or classical, we still don't know. The 2017 proposal can test whether gravity obeys quantum superposition principle.
Yeah, in my opinion,
And our
I
new
think
proposal
some
can
of
test whether
climate
gravity obeys
has to
quantum
be
measurement
climate
principle.
is now. Like
And
it's
these
state
two
is now,
tests
it's
together
it's not
can
yet
take us towards a more
gadgets,
complete demonstration
industrial
of
levels.
gravity as a quantum
Because
entity.
there are a lot of
And also compared to the 2017 proposal, our new proposal has some experimental advantages. So with this, I would like to mention that testing this any particular quantum theory of or this type of classical theory of gravity, you need to create a particle accelerator of the size of our galaxy. On the other hand, the 2017 proposal or our new proposal requires manipulating or preparing some quantum state with nano-sized particles. So obviously, creating this type of manipulating this type of nanoparticles is obviously preferred than creating galaxy-sized particle accelerator. So with this, I would like to thank.
Okay, thank you, Debarshi. So if there are some urgent questions, you can ask. Otherwise, you are encouraged to contact Debarshi by email somehow. If you have questions, if you have queries, clarifications, if you are needed. But if there are like one urgent questions, we can take it. Okay, if there is no such question, so let us thank Debarshi again for this nice talk. And we are ending recording.
Debarshi, it was a very good presentation.
Thanks, Nandar.
Yes. Okay, so that's all for today. So see you in the next meeting. Thank you everyone for joining.
Yeah, bye.
Bye.